3.5, we will discuss and look at examples of exponential growth and decay. So we will actually create mathematical models which represent exponential growth or decay. We will model exponential growth and decay, observing that the specific quantities under discussion either grow or decay at a rate directly proportional to their size. Two examples, for instance, include the growth of, say, world population and the growth of money in an account subject to compound interest. So in this section, we will create functions that model such data and use these functions to make predictions. Okay, exponential growth and decay models. So the mathematical model for exponential growth is given by f of t is equal to a sub 0 times e to the kt, or a is equal to a sub 0 times e to the kt. Now let's investigate some of the characteristics of exponential growth functions. So let's see, if k is greater than 0, the function will model the amount or size of a growing entity. All right, for instance, let's see. All right. Let me just first identify. So k happens to be the constant k representing the growth rate. A represents the amount at a given time t. A sub 0 represents the original amount or size of the growing entity at time t is equal to 0. So graphically, what we're looking at, let's say, with the original amount is a sub 0. All right, when k is greater than 0, we have exponential growth. And we see that the function is increasing. All right, and we said that k is greater than 0, and the function is a sub 0 e to the kt. K is greater than 0. So this illustrates exponential growth. On the other hand, let's consider the case when k is less than 0. So if k is less than 0, the function models the amount or size of a decaying entity. Again, the a sub 0 represents the original amount. A represents the amount at a given time t, and in this case, where k is less than 0, k is a constant representing the rate of decay. All right, the decay rate. Graphically, all right, so the original amount is a sub 0. All right, and over a period of time t, the function, say, does that. We see that it is indeed a decreasing function. K is less than 0. And again, the model then would be the graph of a sub 0 e to the kt. So this represents exponential decay. Let's look at an example. In 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,050. Actually, that should be 2. Should be 1052 million. This is checkpoint number 1. So we're to answer the following question. We're going to use the exponential growth model. A is equal to a sub 0 times e to the kt, in which t is the number of years after the year 2000. We're going to use this to find the exponential growth function that models the data. All right, now, sometimes we need to use the given data to determine the rate of growth, k, the constant k. After we find the value of k, we can then use the given formula to make predictions. All right, so let's look at part A. Let's answer part A. All right, so part A, let's see. The initial population in 2000 is given to be, that's a sub 0, which is what? 807 million. Now, since 2011 is 11 years after 2000, that indicates that t is 11, and A, the amount at that time is going to be 1,052 million. All right, so we're going to use this information to find k, the constant k, which represents the growth rate. All right, so to find k, let's see what we have here. We have A is equal to a sub 0 times e to the kt. All right, let's substitute what we know. All right, the amount is 1052. A sub 0, the original population, is given to be 807 million. And this is e to the kt. But in this case, t is 11, so I make that substitution and get what? 11k. All right? So what we want to do now is to solve this equation for k, the constant k. So what do we have here? We have 1052 divided by 807 is equal to e to the 11k. All right, so we have an exponential equation. We can now solve this. The base is e, so we're going to take, when the base is e, we can take the natural log of both sides. So let's take the natural log of both sides of this equation. So that's the natural log of 1052 divided by 807 is equal to the natural log of the right-hand side, the natural log of e raised to the 11k. All right, now upon simplifying, what do we have? We have the natural log of 1052 divided by 807 on the right-hand side the natural log of e to the 11k is going to be 11k times the natural log of e, which is what? Just 11k. We know that the natural log of e is 1. All right? Now, let's solve for k. All right? To get k, we have the natural log of 1052 divided by 807 and divided by 11 would give us k. All right, now if you use your calculator, you see that to simplify, we get a numerical approximation for k. K is approximately 0.024. All right, so the growth rate k is 0.024. All right, so the growth function, now we can write the growth function. So therefore, the function is given by a is equal to a sub 0, 807 times e to the kt. But now we know that k is 0.024 t. All right? So that's our growth function. In part B, the question is, by which year will Africa's population reach 2,000 million or 2 billion? All right, so we have our growth function. The growth function, again, is A is equal to 807 times E to the 0.024 T. All right, now in this part B, we have to find T. All right, so by which year would the population reach 2,000 million or 2 billion? So in other words, in what year will A be 2 billion or 2,000 million? So A in this is 2,000 million. So we substitute, and now we solve it. 0.024 t. All right, let's simplify. I can divide both sides by 807 is equal to e raised to the 0.024 t. So we have an exponential equation involving the base e. So what do we want to do now? So we want to take the natural log of both sides of the equation. So the natural log of 2,000 divided by 807 is equal to, again, the natural log of e raised to the 0.024 times t. All right? So we have the natural log of 2,000 divided by 807. All right, the natural log of e raised to the 0.024 t power is going to be just the x, 0.024 t. All right? And now solving for t, dividing both sides of this equation by the coefficient of t, which is 0.024, we have the natural log of 2,000 divided by 807, all divided by 0.024. And if you use your calculators, we get that t is approximately 38. All right, so therefore, to answer the question, Africa's population will reach 2,000 million approximately 38 years after 2000, which would bring us to what? 2038. Our next example involves exponential decay. All right, so what we have here, the problem is the half-life. And what do we mean by half-life? The half-life of a substance is the time required for half of the substance to decay or disintegrate. So the half-life of lead is 22 years. How long will it take for a sample of this substance to decay to 80% of its original amount? So the first thing we want to do is to find the decay equation. Okay? So we're going to use the given information. So half-life, so the amount in 22 years would be half, whatever that is, so that's 0.5, half of the substance, is equal to E to the KT. All right, so we have 0.5 is equal to, and we know that the half-life is 22. So in other words, T is 22. So we get E to the 22K. All right, so we're going to solve this exponential equation. All right, so it's the natural base E. So the next step, we're going to take the natural log of both sides of the equation. So that's the natural log of 0.5 is equal to the natural log of E raised to the 22K power. All right, so this is the natural log of 0.5. The right-hand side simplifies to 22K. It's 22K times the natural log of E, but again, we know that the natural log of E is 1. All right, so now we can find K. We're going to divide both sides by the coefficient of K, which is 22. All right, so this is all equal to K. And using your calculator, we get that K is a negative 0.031,507. All right, so the decay equation then becomes A is equal to E to the K T. But K is a negative 0.031507 times T. So this is our decay equation. All right, so we still need to answer the question. So we're going to use the decay equation to answer the question. All right, so let me just rewrite up here the decay we have. A is equal to E to the minus 0.031507 T. All right, and the question is, how long will it take for a sample of this substance to decay to 80% of its original amount? So we're going to have A, it's going to be represents 80% of the original amount. So 0.8 is equal to E to the negative 0.031507 times t. All right, now we can solve this exponential equation for t. So the first step, as you recall, we're going to take the natural log of both sides. So this is the natural log of 0.8 is equal to the natural log of e to the negative 0.031507 times t. And what do we get? We get the natural log of 0.8. The right-hand side simplifies to a negative 0.031507 times t. All right, now we can solve for t by dividing both sides by the coefficient of t. So what do we have? We have the natural log of 0.8 divided by a negative 0.031507 is equal to t. And if you use your calculators, you get that t is approximately 7.1. So now we can answer the question. So therefore, it will take 7 years for a sample of the substance to decay to 80% of its original amount. And of course, this is in years. Now, the logistic growth models. In these examples, we take into account the fact that growth is limited, is always limited. Nothing on earth can grow exponentially indefinitely. So the logistic growth model is a function used to investigate this situation. And the logistic growth model is given by f of t is equal to c divided by 1 plus a times e to the minus bt, or a is equal to c 1 plus a times e to the minus bt. All right, so here f of t given as a function of t, the time, where A, B, and C are constants with C being greater than 0, and of course as well as B. Both C and B are greater than 0. All right? So basically, graphically, what we have to illustrate this limiting value, the growth rate of a substance. All right, so let's say we begin here. This is the original. And the logistic growth model illustrates that the function begins to increase. So let's see. And then it begins to level off. All right. So this is the increasing, it's increasing rate of growth. And it begins to slowly level off, decrease, and it approaches this horizontal asymptote. All right, this horizontal asymptote, which actually turns out to be, let's say, if you go back to the original function, so this is a horizontal asymptote. All right, so if we go back to the original function and consider what happens to the function as t increases. All right, so as t increases, this term, a to the e to the minus bt, approaches 0. So you have c over 1 plus 0, so a is actually getting closer and closer to c. So this means that the horizontal asymptote, which is y is equal to c, is the value of a, where a can never exceed this value. All right, because that's a horizontal asymptote, and it will never exceed. So C, then, we can conclude that C represents the limiting size of A. All right? All right, let's look at an example of the logistic growth model. This is actually checkpoint number 3 from the text. All right, so in a learning theory project, psychologists discovered that the function given by f of t is equal to 0.8 divided by 1 plus e to the minus 0.2t is a model for describing the proportion of correct responses f of t after t learning trials. So the first part, we are to find the proportion of correct responses prior to learning trials taking place. All right, so in part A, all right, we know that, all right, the time prior to learning trials corresponds to what? Tells us that the time is 0. That corresponds to the time prior to the learning trial. So t is equal to 0. So in other words, then we need to find f of 0. So f of 0, using the given function, we have f of 0 is 0.8 divided by 1 plus e raised to the minus 0.2 times t power. All right? And if you use your calculator here, you will see that this is approximately 0.4. So the proportion of correct responses prior to learning trials was 0.4. All right, in part B, find the proportion of correct responses after 10 learning trials. All right, so in other words, this time, I'm going to substitute 10 for t in the model. So we're going to substitute, all right, 10 for t. So what do we have? So we want to find f, and this is part B. So we need f of 10, all right? So f of 10 is going to be 0.8 divided by 1 plus e to the minus 0.2 t. All right, and if you use your calculator here, this is just a division line. If you use your calculator, we get that this is approximately 0.7. So to answer the question, the proportion of correct responses after 10 learning trials was 0.7. Part C. What is the limiting size of f of t, the proportion of correct responses, as continued learning trials take place? All right, so we recall that from the logistic growth model, f of t, I'll put it over here, part C. We know that f of t is c divided by 1 plus a to the e A times e to the minus bt. All right, the constant recall from the graphical illustration of the logistic growth model that the constant c represents the limiting size that f of t can attain. So, in this case, the limiting size of the proportion of correct responses as continued learning trials take place is going to be C, which is what? 0.8. So, all right, in this example, we want to model cooling over a period of time. Let's say you have a cup of coffee or a cup of tea. Over time, the tea or the coffee cools to the temperature of the surrounding air. All right, so we're going to use Newton's law of cooling, which states that the temperature of a heated object decreases exponentially over time towards the temperature of the surrounding environment, of the surrounding medium. So Newton's law of cooling is given by, it says that the temperature T, so, all right, the temperature T of a heated object at a time T at a given time T is given by T is equal to C plus T sub 0 minus C times e to the kt, where, all right, we know that T is the temperature, where C is the constant temperature of the surrounding medium. So C is the constant temperature of the surrounding medium. All right. T sub 0, all right, is the initial temperature of the heated object. All right. And K, all right, K is going to be a negative constant that is associated with the cooling object, cooling. All right, so let's look at an example where we actually apply Newton's law of cooling. All right, the example that we want to consider reads as follows. An object is heated to 100 degrees Celsius. It is left to cool in a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. All right, part A, we're to use Newton's law of cooling to find a model for the temperature of the object after T minutes. All right, so let's see. We recall that Newton's law of cooling is given by T is equal to C plus T sub 0, the initial temperature, minus C times e to the KT. Now in our problem, the temperature of the object is 80 degrees Celsius. So we have 80 is equal to C. C in this case is 30. All right, so we have 30 plus the initial, all right, is heated to 100 degrees Celsius. So we have 100, that's the initial temperature, 100 minus 30 times E to the KT. But in this case, we want to know after 5 minutes. So T in this case is 5. And now let's simplify. So we have 80 is equal to 30 plus 100 minus 30, 70 times e to the 5k. All right, solving. If I subtract 30 from both sides, I get 50 is equal to 70 times e to the 5k. All right. And so simplifying 50 divided by 70, I can simplify, that's 5 over 7, is equal to e to the 5k. All right, so now we want to continue to solve the exponential equation. 5 divided by 7 is equal to 5 raised to the 5k power. All right, so again, we have the natural base e. So we're going to solve this exponential equation by taking the natural log of both sides. So we get the natural log of 5 over 7 is equal to the natural log of e to the 5k. All right, simplifying, the natural log of 5 over 7 is equal to 5k. Now, therefore, the natural log of 5 over 7 divided by 5 will give us k. Again, using your calculator, we get that if you simplify, we get k is equal to a negative 0.0673. So therefore, T, all right, so T, let me just rewrite, so we get T is equal to 30 plus 70 times e to the k, and in our case, k is a negative 0.0673 times, what is the temperature after 20 minutes? So in this case, so it's going to be 20. All right, so we're going to substitute 20 there. All right. And if you simplify all of this, 70 times e to the minus 0.673 times 20, you will get that T is approximately 48 degrees. All right, now to answer the question, after 20 minutes, the temperature will be 48 degrees. All right, I'm going to leave part C. Why don't you continue? I'm going to let you answer part C. When will the temperature of the object be 35 degrees? You're to work on part C. If you have any questions, please post them to the discussion board.